Our research is on controlled source electromagnetics, CSEM, monitoring of hydraulic fracturing, wellbore, and fluid effects. CSEM systems transmit electromagnetic energy into the subsurface, and as that energy propagates into the Earth, geologic features in turn create a secondary response recorded by receivers on the surface. This method allows us to measure the geoelectrical signature of our area of interest. We present a terrestrial unconventional model with varying vertical and lateral wellbore extents and depths, along with subsurface conductive fluid mapping. The code used is forward modeling algorithm developed by Badea et al., and the motivation for this work is to apply CSEM monitoring to unconventional plays to better understand wellbore electrical signatures and the flow of electrically conductive fluids out of and around the wellbore.
The code that we used uses 4 distinct models, which can be shown at the top of our results section. So the first thing we wanted to test was the effect of a vertical wellbore. And so our first plot right here in figure 6, our black curve is denoting our primary electromagnetic field response, which is if there is no vertical wellbore present, and then this red curve is showing the total electromagnetic field response, which is the presence which has the presence of a vertical wellbore. And so what we can see from this plot is that if there's a vertical wellbore present, there's a substantial increase in the electromagnetic response. The next thing we wanted to test was the vertical extent of that wellbore. So we're looking at this geoelectrical model, and we basically vary the distance between the transmitter and the end of the vertical wellbore. And what we can see from this plot is that changing the extent of these vertical wellbores doesn't have a very large impact on the electromagnetic response. The next thing that we wanted to investigate was the effect of a lateral wellbore. And so the first thing we tested with a lateral wellbore is the depth variation. And so we're looking at this geological cross-section, and we're manipulating this Z1 value, which is going to be the distance between the transmitter and the lateral wellbore. And in this plot, our black curve is showing our most shallow lateral wellbore, where our yellow curve is showing our deepest lateral wellbore. And what we can see from this plot is that as we increase the distance between the transmitter and the lateral wellbore, we see a decreased amplitude response, in addition to receiving the signal at greater offsets. The next thing that we wanted to look at was the lateral wellbore toe effect. And so basically we're looking at this map view figure, and we're manipulating this XL value, which is going to be the distance between the transmitter and then the toe of the lateral wellbore. And so what we can see here, the black curve is denoting our shortest lateral wellbore, whereas our orange is going to denote our longest lateral wellbore. And so what we can see from this plot is as we increase the distance between the toe of the lateral wellbore and the transmitter, we see a decreased amplitude response at mid-ranges, and then at larger ranges, we actually see an increased response. Now there is some ambiguity within this plot because our mid-range toes of 2,000 and 6,000 meters actually don't follow that same path, and so that requires some further investigation as to why it doesn't follow the trend. The last thing that we were looking at was fluid spreading. So we're dealing with this figure 5 up here, which is the same as a previous model other than the fact that we added in 2 blue blocks, which denote the fluid-filled fracture zones, the volume of that fluid. And what we see in this plot, our black is going to be the smallest volume, and then our yellow is going to be the largest volume. And what we can see is that as we increase the volume of the conductive fluid-filled fracture zone, we see an increase in the EM response as expected. The next thing we wanted to test, so this was with constant injection of that fluid, the next thing we wanted to look at was if we stopped the injection. And so what we can see with this plot is as we increase the volume of the conductive fluid, we first see a spike in the EM response, but then as we continue to increase that volume, the EM response actually decreases.
And for future work, we are going to develop a complete 3D model of hydraulic fracturing system, including vertical wellbore, lateral wellbore, fracture propagation, and fluid migration. We are going to investigate the effect of changing the offset between the vertical wellbore and the transmitter. Now we are going to remove the effect of the wellbore from a conductive fluid spreading test to see whether the effect is due to wellbore fluid coupling or is it just because of fluid-filled fracture zones. Then we are going to use geomechanical modeling to develop more physically accurate shapes and movement of conductive fluids through fracture zones. And finally, we are going to compare the CSM response with the microseismic data.